Hey guys, welcome to another video. So this is the third video in the series where we deal with binomial theorem identities. So if you haven't already done so, please look at the last two videos, subscribe to the channel if you haven't done so, also like the videos, share it with your friends. These videos are free, no ads on these videos, so just get the message out. If someone wants to learn about these topics, please feel free to share these videos. So the first video in the series sets forth a framework on how we prove binomial theorem identities. So the types of questions that we saw in the first video mainly related to substitution, where if you ever see something that you have to prove and the numbers are all that remain, there's no x's, there's no values of n's, and they've done something with those variables by subbing in constants, right? First video. Second video. Now, I went on a bit of a rant in the second video where because it dealt with calculus, a lot of teachers that in Sydney, in New South Wales, that follow the NESA guidelines, right, teach binomial theorem in year 11, right, before they learn calculus. And then they have to reteach it again in year 12 because the calculus questions are there. I mean, just seems a bit broken and for me a bit nonsensical, right? Like, why don't you teach binomial theorem, which is a hard topic, right? Unrelated to most other topics, maybe a little bit to combinatorics, but not really. You can teach it, separately, and teach it all at the end when you've learned integration, when you learned differentiation. It just makes a lot of sense. But some teachers don't do that, or most teachers don't do that now with NESA's guidelines, etc. So I'm confused, but here we are. So that was the second video. We dealt with differentiation and integration. Hopefully they weren't too bad. And in this video, I mean, technically speaking, and just in terms of explaining from a teacher or a tutor to the students, this lesson is probably the hardest in terms of technique, right? And it's also the last one in terms of new technique that we'll explore. I do have one more video in this series planned for next time where I explore harder questions from the HSC from past papers, which deals with which utilizes a number of techniques that we've shown in the last two videos and this video. So let's dive right into it. So today we're going to explore binomial theorem identities using theorem identities using comparing coefficients, right? Comparing coefficients. So wind back to probably the most important formula you need for this part, the expansion or Pascal or Newton's formula using combinatorics, where we subbed in sub A and B, or x and y, we use 1 plus x. So that gives me nc0 plus nc1x plus a nice little polynomial that gets derived at should be x squared there, plus nc3 x cubed plus all the way ncnxn, right? Nice. Right. Nothing too outrageous about that. All right. So we started off with that last time in the last two videos. Most of the questions require you to start from here or consider this as a start. Now, comparing coefficients, right? Let's start with a very simple illustration, right? Simple illustration. Sometimes the teachers ask you to prove certain things by comparing coefficients in this topic. What does that mean now? The best way to understand it is, let's take a very simple expansion, right? Now we know if I expanded this using Pascal's triangle, I get like 1 plus 3x plus 3x squared plus x cubed, right? 1, 3, 3, 1. Nice. However, that's not what we're dealing with here, right? We want to expand this using the combinatoric expression. So what we're going to do, you can sort of see, right? They've replaced the 1, the 3, and the 1 with combinatoric expansions, right? So nc0, so in this case, n is 3, so 3c0, 3c1, 3c2, and 3c3, right? So the way I'm going to do it, maybe I'll just not squash it all in. Let me write this 3c3, x3. Great. Is that okay? So with that in mind, right, what we're going to do today is basically use binomial expressions like this guy and then get it expanded using Pascal's or Newton's formula. Now, What I want to show you now is 1 plus x to the power of 3. That's not the only sort of binomial expansion that we can derive, right? So another way to express 1 plus x cubed, 1 plus x all cubed, is to basically go, well, what if that was like 1 plus x squared, sorry, 1 plus x squared times 1 plus x, right? Here we have binomial, two sets of binomial expressions, product, right? Multiplied together. So what I want to show you is by having sort of two binomial expressions, I'm going to individually expand that and that. Now we know, right? 1 plus x squared, sorry, I'm trying to leave a bit of space. 1 plus x all squared gives me a nice perfect square that looks like that. And obviously 1 plus x looks like that, right? What I'm going to do, let's replace all the coefficients with the pink box combinatoric terms, right? So 1 goes, 2 goes, 1 goes, 1 goes, right? And let's replace this with 2, because this is power 2, right? 2c0, 2c1, 2c2. Sorry, I'm trying to squeeze it in, but I can't fit it. Plus 2c2. Now, and on this bracket, because it's parallel 1 essentially, right? That's like 1c0, 1c1. Now, what am I trying to show you? What if I now asked you, right? Let's use a different colored pen to go, what if I asked you to find me the coefficients of x squared, right? X squared is over here, and the coefficient of x squared, in this case, right? Is that black term there, 3c2. Now, since the blue is the same expression, let's try to get the coefficient of x squared by expanding these two binomial brackets, right? Now, I can see to make x squared from these brackets, I need to multiply this term here, because it's got the x with this term here, right? Because x times x is x squared. So that times out using expansion, or I like to call it rainbows, right? That will give me x squared. Another way to get x squared is by multiplying the x squared term with the constant, right? So I got two ways in the blue line to get x squared. So let's see, right? Let's see. Coefficient. Poor handwriting. Of x squared. How can I get it? So if I did the first rainbow, right? The first arc here, 2c1 times 1c1. Plus the other way, 2c2, 1c0. Now, what am I trying to show you? So if this question was a question in an exam, they will ask you either to prove that the black equals it. So prove that this equals to this, right? They're equivalent. So prove, in this case, we've demonstrated, right, that 3c2 is equivalent in value to this plus this, right? That's something that they're going to ask you to prove by looking at coefficients. Now, and this also makes a lot of sense because I know on my calculator, this guy, 3c2 is 3. And I know that this guy is the same as 2 times 1, and this guy is the same as 1 times 1, which is 3, right? That's equivalent, so that makes sense as well. So what are we trying to do in this part of the topic? We are going to do two comparisons, right? So we're going to do one comparison of two things. One, we're going to compare this green line, right? Where it's 1 plus x to the power of the original power 3. And then we're going to compare it to the blue, which breaks down that 3 into a combination, in this case of 2 and 1, right? By having two binomials, I then get this rainbow action, right? Where on one side, I have a whole string of numbers. On the other side, I have one term. You're going to see a lot of that in the sort of hardest technical part of this topic. Now, that's enough talking for me. Let's see a question in action and you'll know what I mean, right? We're going to apply very similar theory to here. So, Sydney Grammar, 2008. Look at this question, right? In the question, it says, using the identity, so they broke up in this case, right? They broke up 1 plus x to the power of 100 into 2 parts. Can you see that? In this case, they specifically didn't choose a symmetric breakup. Instead of 50-50, they chose 4 and 96, right? Okay, cool. Where 1 plus x to the power of 4 is that, and 1 plus x to the power of 96 is that. That's fine. And look what they want you to prove, right? Yeah, they want you to prove something that has, well, I'll highlight the one, yeah, and then something that has a longer expression, right? There's always a long and a short, always a long and a short. Just keep that in mind, always a long and short, yeah? So let's go down this path. I'm going to start with the right-hand side, right? Let's start with the right-hand side. So the right-hand side here equals to 1 plus x to the power of 100, right? And using my combinatoric expansion, so you know what? I'll be referring to it, so why don't I just copy, let's paste that as picture. So I can shrink it. Almost like pocket size, right? So pocket size over here. So that pink box is what I'll be referring to. So guys, let's expand this. So just sub 100 in, so you get 100. Now I'll write the combinatoric expansion just like the expression like them. So 100 C1 C0 plus 100 C1 plus x plus 100 to. Hey guys, for this one, I'm gonna do a few more because it's important. I'll go up to 4, right? Just to really, yeah, get to the main game there. And then plus 100. 100. So 100. Is that okay? That is a straight application of that pink, right? Just subbing in, no substitution. Easy. All right. That's the right-hand side. Now, the left is cool, right? The left-hand side comprises of 2 brackets. It's got 1 plus x, power of 4, and it's got 1 plus x to the power of 96, right? 2 binomials. So for the green, because it's only power of 4, we're going to write all of them. There are 5 terms, right? For the pink, we'll write maybe the first few and then leave out the rest, right? So check this out. So for the green, right, it's going to be n, not n, 4. C0. Sorry, let me put a big square bracket. Yeah, plus 4c1x plus 4c2x squared plus 4x cubed plus 4x4. Great. All right, that's a pink, that's a green expansion. Now the pink, same deal, right? It feels a bit tedious, but there is an important message, right? Important finding plus 96 2x squared 96 3x cubed 96 4x4 plus ... all the way to 96 x 96 square root. Now this is great. So here's the punchline, right? How do I prove the thing they want me to prove, right? What am I trying to do? Look at this, right? Here's the giveaway. See this 100C4? That's the only one where the top number is 100, right? Only one with top one numbers. Where is that? Right? I always ask my class, find it in the blue and the green and pink. Where is it? It's here. Right, there it is. So what have they done, guys? What have they done? They have compared the coefficient of the blue to the green. They've compared the coefficient of x4, right? Because that's the blue. And then where are these numbers? The rainbows of the green and the pink. Yeah. So what I'm going to do for the right-hand side, I'm going to basically go for this one, coefficient of x4. Now, why x4? Because I can see it. The 104 is a giveaway, right? Is 104. That's the right-hand side. Now, you're probably thinking right now, where's this 1 come from? Well, actually, the 1 comes from the left, and they've thrown it over, right? You'll see that in a second. So how do I expand rainbows, using rainbows, to get x4 with the green times the pink? Very easy, guys. Now, obviously these guys here are too big, right? They're too big. X96. I mean, I don't want them. I only want X to the power of 4. How do I get that? Now, how do I get that? X, this one's got no X values. It's just a constant. I multiply that with X4, right? That will give me a power of 4 expression plus this guy times that, because that's X and that's X cubed. That will give me X4. X squared times X squared. That'll give me X cubed times X and then X4. There are 5 rainbows, right? 5 summations, right? So in this case, coefficient of X4 is going to be 40 times 96, 4, right? Plus, I'm just doing the coefficient. I don't need the X4, right? Just need the coefficient. 41 times 96, 3. 42 times 96, 2. You can see it, right? You can see we're developing the expression that I need in the question, right? 96, 1, last comparison, 4, 4, and 96, 0, right? And what can I say now? If both of these are equivalent, the blue equals to the green in the first place, and now I've shown that this equals to this, I can set them equal to. Now, one little catch, right? Where's that 1 come from? Guys, if you scan through, right, if I zoom out a bit, if you scan through and tick off the things you have, 90, 94, that's this guy. This guy is here. This guy is here. This guy is here. So what haven't they done? They've basically replaced anything with 4C0, that's 1. So that's gone. That's why there's only 1 term at the start. And also this term here, we know that 4C4 is 1. 96 C0 is 1. 1 times 1 is 1. And then they've thrown it over the fence, right? So theoretically, if you wanted to show your teacher that you go, therefore, comparing coefficients of X4, I can say, yeah, this guy's 1. So 96, 4 plus 41, right? 96, 3, 4, 2, 96, 2 plus. It's a bit tedious, but important. Now, plus this one's 1 equals 2, and on the right-hand side, 104, right? And then, just for your sake, this guy then gets removed and put over here to get exactly what I want. How's that? That was what, how many marks? 3 marks in a trial paper, right? So by comparing coefficient, how do you know this is a comparing coefficient question? By this identity, right? If they ask you to split one binomial to the power of 100 into 2, you're going to use rainbows, you can compare coefficients, right? That's how you roll. So let's move on to another question that is, well, the most common of these types, right? But it's also a little bit harder when there's less numbers involved. So let's do one more, right? Now I just picked this. This is for St. George 2014. You can go to so many past papers and see these questions. There's, Gosford had one in the last 10 years. All these schools have HSCs has this commonly, CSSA. Guys, you can see the structure and the bones. They actually tell you. They tell you by equating the coefficient. They tell you which one to look for, right? In this case. So let's see. This is the right-hand side, and just like before, there's a green and a pink. Right? Prove that. Now, once again, before I do this, right, I want you to explore this fun fact, right? So fun fact, did you know that the combinatoric of n ck is equal to n minus k, right? It's reflected, because if you look at Pascal's triangle, it's symmetrical, right? 1, 3, 3, 1, 1, 4, 6, 4, 1, it's always symmetrical, right? Now, if you had to prove this fact, right? If you had to prove this fact, this is how you do it, right? You basically go, the left-hand side is clearly NCK, and we know with our factorial expression is top factorial, bottom factorial, top minus bottom. And then the right-hand side is going to be n minus k, factorialize top factorial, bottom factorial. And this is just needs a little bit of work, top minus bottom factorial. And guys, hopefully you're all okay that n minus k, n's cancel out, that's just k factorial. With that, that's just the left-hand side, right? So therefore, done. Yeah, so that's the thing. Now, why is it, what does that mean, right? What does that mean? It means that for any combinatoric expansion, right? Any binomial expansion, it's symmetrical. So whatever number, let's say, for example, n was like 10, right? Whatever number you put in here is equivalent to 10 minus 2, 8, right? They're equivalent. What else does this mean? 5, 3 is the same as 5. If the top number is the same, then the bottom number is 5 minus 3, so it's 2, right? It's all symmetrical, all good, right? That's what it means. Now, why am I telling you that? Because we need it for this question, right? Implicitly, as part of the proof, we need it later. So keep that fun fact in blue box up your sleeve. Now, where's my pink box, which kickstarts this? This guy here, let's take it, put it here once again, fun fact. So I've got a pink box, pocket size, and a blue box recently derived. Let's do this, right? So let's expand the blue first, or get an expression for 1 plus x to the power of 2n. 2n, right? 2n is even. That's important, because when binomials expand, if that's an even number, if that's even, right, then how many terms do I have? I actually have odd terms, because if you think about it, if that was squared, I got 1 plus 2x plus x squared. It's actually, there's 3 terms, right? If that was power of 4, I get 5 terms. So I guess what I'm trying to say is, if it's even, right, you should get this, right? Yeah, 2n C0. Oops. Actually, let's do it in the form that they do it, right? Yeah, 2n C0 plus 2n C1 plus, yeah, now this goes all the way, right? Now, do I wanna, yeah, let's do one more. Oh, sorry, I forgot the x. Plus 2n2 x squared. Yeah, plus dot, dot, dot. Now, guys, just for your context, because this is asking me, in the question, it's already told me, right? It's told me to compare the coefficient of x, n. I'm just gonna put that term in the middle, right? So where's n? N is like sort of halfway in here, 2n cn xn, right? That's not the last term, that's bang smack in the middle. So what I'm going to do, can I just move this blue fun fact and the pink over here in the corner, park it there. All right, we'll come back to it. All right, we won't forget it. It's there. It's there. Now, with this one, I'm going to then, so that is in the middle. I'm just going to add a few more terms just for demonstration. It's just easier if I do it. So plus 1. It's easier if I do it, because then it's easier for me to explain. Plus dot, 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 plus the ones at the end, right? Now, I won't just go 2n, 2n. Let's put a few in there, right? So 2n. So the third last one is 2n minus 2, right? X 2n minus 2 plus, it looks a bit long, but I just want to put it in there, right? Let's just put it in there. Yeah, some teachers, when they explain this, they skimp on the working out, and then they regret it, because then they're like, oh, I just picture it. And then kids can't picture it, right? So I'm just going to put it in there. 2n x 2n. Now, so that's long and winded, but what is important is it's symmetrical, right? Why is it symmetrical? So is it symmetrical? No. This one's in the middle. So actually, you know, I did too much. I don't actually need this one. Yeah, because like I said, if it's even, there's one in the middle, right? And these ones here, don't need that. So let me get that back. I've done too much, right? Done too much. Didn't need that extra one. Cool. All right. So there's one in the middle, and then everything around it is symmetrical, right? So it folds on itself. All right. Let's see now. in this question, it wants me to compare xn. It wants this guy, right? So coefficient of xn is 2n n. Oh, that's cool, right? That's cool. Now let's see. Yeah, now let's see. So, and just, yeah, maybe before that, you're probably thinking, well, why is this not here? It's because they re-express this in combinatorial terms. So this in its factorial form is top factorial, bottom factorial, top minus bottom. And if you look at that, n factorial, where's that? That is this, isn't it? Yeah, so sneaky of them, right? To basically put it in factorial form, just to make it look a bit different, but it's not. There it is, right? So I've got the right-hand side done, nailed. I just need to expand now the green and the pink and to make it look like that. And this is where that little fun fact on the right there is going to be helpful. So let's go green. Right. Go green. Right. This is where I really utilize my color palette on PowerPoint, right? So what's the green times the pink? So I know that green and goes to n pink 1 plus x to the power of n. Now, let's go green first, right? So equals 2. Green says, remember, I want the full, the pink expansion of this now. This is your classic NC0, 1, 2. Once again, don't skimp. I want 3 on the left, 3 on the right, right? I need 3 and 3 just to demonstrate point. Yeah, maybe I didn't need it on the blue. Sorry. But for the green and the pink, definitely. Yeah, I need to demonstrate point. Plus n minus 1, xn minus 1, plus nn xn. Now I'm going to try something, right? I've never done this before. But here we go. I'm going to just copy this because the pink is exactly the same, right? That's the green. See if I can copy it, and then I'm just going to see if I can put it right next to it and just change the color. It's very sneaky. I apologize, but oh god, no, that's red and pink. Does that work? Oh yes. There you go, right? So if you expanded it, I mean manually, it'd take a bit longer than what I just did there. You get the green and the pink, right? Now, where are my coefficients of xn, right? This is the hardest part, right? For your teacher to explain this. I've done this a few times, right? Explain it. And if I hadn't had drawn out the green and the pink as much as that, my students get confused. So for you, hopefully this makes sense now. If I was to use rainbows, right? Expansions to get xn, where are they? Constant times this guy, that's the first one. X times x to the power of n minus 1, because that's like 1 less, and together with the x, it becomes xn. Oh, I forgot. Oh man, that means I did mistakes on both sides. This one's x to the power of 2. And on the pink as well, it should be x to the power of 2, right? So that means this squared times a 1, that's 1 less, that will give me it. And then dot, 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 right? This guy times a squared, this guy times a x, this guy times a constant, right? So you can see I have a string of numbers that multiply together, right? That gets me xn. So if I deal with this, right, coefficient of xn, the first big rainbow would be n0 times nn, plus the second one will be n1, n minus 1. The third one would be n2, n minus 2, plus dot, dot, dot. And it's these guys reflected, right? Yeah. Now for this purpose, I probably don't need the third last, second last. I'll just go to the last one. So n 0, because you get pattern, right? You get the pattern. Guys, right now I have, this is the right-hand side, done. Look at the left. That looks a little bit different to this. Why? Because of that fun fact in the blue box there. Now, I need to, how do I get the squared in? Can you see, right? Every time you see the second bracket, n as an example, using the reflection property, I know that this guy is equivalent to n minus n, which is 0. Every time I see this guy, right, n minus 1, this guy becomes n, and n minus 1 is just 1. This guy. Reflection property up there says n minus 2, which is 2. And so on and so forth. This guy at the end. Using the reflection property up there, that's n minus 0, which is n, right? So therefore, what I can demonstrate is that this is going to be n times n, nc0 times nc0, so nc0 squared, n1 squared, n2 squared plus dot 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 n squared, using this reflection property upstairs. And then I got it, right? Once I have that, then this guy is the left, that equals to the right. And all I have to do to finish this proof off is to go by comparing coefficients of xn, n0 squared, right? n1 squared, n2 squared, n squared equals to the right hand, which wasn't a combinatoric term. They made it into factorial form, n factorial, just to be sneaky. Boom. Yeah, so I guess the explanation for this, I mean, conceptually, it's just a bit tedious, right? It's just, sorry, mechanically and practically, it's a bit tedious. Conceptually, it's not easy, right? Yeah, you have to, for teachers out there, if you want to teach this, do not skimp on the rainbows. Have 3 to the left, 3 to the right, because when you expand it, it connects, right? It connects, and then it lets your student see it better. Otherwise, if you skimp, your students don't necessarily see where the rainbows connect. Guys, comparing coefficients, that's how you do it. There are harder questions. I'll try to deal with some of these in the next lesson. Guys, hopefully you like that. If you do, please give me a like, subscribe, tell your friends, and I'll see you in the next video. Thank you.